Okay, for this last module, I want to kind of go through and talk a summary about stars. So we have already talked about the proton-proton chain reaction. So in the nuclear physics, remember we did the conversion from hydrogen to helium, where 4 hydrogens is slammed together to make 1 helium plus a whole lot of energy. So this is what's going on inside of stars. So stars produce energy by one of 2 ways. So they produce energy by the nuclear fusion, and they produce energy by getting smaller. And you're like, well, how can that? What's going on with that? Well, if they're getting smaller, think about it, if you were having like a family reunion or something, you have 30 people, and instead of being all spread out in the backyard and everywhere, you all went to the kitchen. So how hot would it be in the kitchen? So it's going to be getting warmer and so forth. So they're producing energy by getting smaller, and they're producing energy through this nuclear sense. So the radiation coming from the sun. So the nuclear radiation coming from the sun, and the stars produce everything. So remember the electromagnetic spectrum. I'm going to post websites about this so you can see the sun from all the different wavelengths. The sun emits radio waves, gamma rays, X-rays, UV light, visible light. We see that infrared, you name it, it produces. The sun emits, and that's how you can get a rainbow. Is the sun, the light coming off the sun is actually white. It's yellow based off of color, which I'll talk about here in a second. But sunlight is white light, which is a combination of everything in the spectrum. So you see when it separates, you get the red, orange, yellow, green, blue, indigo, violet. So that's how you get all the colors of the rainbow, is because of the white light of the sun. Now the sun is yellow. Oops, didn't mean to hit that. The sun is yellow. So when you look at the red, orange, yellow, green, blue, indigo, and violet. So remember we talked about this as high energy here, and this is low energy. Well, low energy is going to be cool, and high energy is going to be hot. So violet stars are hotter than red stars. We have a yellow star. Thankfully, we don't have a green star, blue star, or violet star. Our sun would be too hot, and a red star would be too cold. But I want to look at Orion. This is the constellation Orion. Let me trace it out a little bit. You've probably seen it in the nighttime sky. Beautiful constellation. But I want to look at these 2 stars right here. So this is red. This is Betelgeuse. Oops, spelled that wrong. E-U-S-E. Sorry about that. And this is Rigel. Rigel is a blue star. So this is one of the hotter stars around. And this is a cold star. When I say cold, we're talking about like 3,000 Kelvin. So not very cold relative to the other stars, where this star is probably like 30,000 Kelvin, something like that. So our sun is like 10,000 Kelvin. So we're not talking about things that are super hot, super cold. Everything's hot compared to what we're dealing with, but relative to each other, red stars are cool, violet stars are hot. So that's how we tell the temperatures of stars. We can't go actually touch the stars, but we look at the color of their surface and look and infer the temperature from that right there. And then we can look at the chemical makeup and spectroscopy and stuff like that. So again, I'm going to post lots of videos so you can see X-rays, gamma rays of the stars and stuff like that. So it's a really neat phenomenon. If you would love to study this more, I would encourage you to take an astronomy class. Just because of the limits of this course, we really can't get into this material too deep. If you want to study stars and stuff like that, that's Astronomy 1020. Where you're going to spend an entire semester looking at everything beyond the solar system. Stars, black holes, supernovas, all that really awesome stuff there.